Hello AP Calculus students, Mr. Ford here with another homework tutorial. This is 3.4.2 of the CPM AP Calculus curriculum. We're going to be doing every problem in the set, but we're going to be making some modifications along the way because, we'll make some of the questions a little easier by giving a couple of alternate instructions. So, 3.161 you're going to want some space for. This is a good repetition of a really common AP Calculus practice, which is to write the equation of a line tangent to a curve at a point. Here they've given us 2 points, x equals 0 and x equals 2. So in order to do this, we have to remember that the general, I'm going to work off to the side here. I suggest you do this work maybe on a separate piece of paper with the problem in front of you. So our original function, y, is equal to x to the third minus 4x. For the line, or the equation of the line, what we're going to need, if you think about the AP Calculus version of this, we're going to need to know what f of a is. That is what happens when we plug in 0 or 2 into that original function. We're also going to need to know what f prime of a is, because that will be the slope. So we'll need f prime of 0 and f prime of 2, and x minus 0 and x minus 2 will go there also. So we're going to do this twice. Let's do the version where x equals 0 first, because that will be easier. In this case, the first thing we need to know is what y is when x is 0, which is incredibly easy to do. It's just going to be 0. So we know that the point 0, 0 is going to be on this curve. The next thing we need to know is the derivative. Y prime is going to be equal to 3x. Actually, let me write this up here underneath this, because we're going to use it in both problems. This is going to be 3x squared minus 4, like that. So we need to know what y prime is when x is 0, which is also very easy to do. It'll be 3 times 0 squared minus 4, in other words, negative 4. So now we can actually build the equation of the line, because we're going to use this general skeleton over here, but we're going to plug in the information that we know. So when x equals 0, here is the equation of the line. It will be y minus 0 equals negative 4 times x minus 0. Or in other words, if we clean it up a little bit, y equals negative 4x. That's the first line that we will figure out. I'm going to go ahead and box this work up so we can kind of organize our thoughts here on the page. Let's do when x is 2 next. It'll be kind of the same process. First thing we need to know is what y is, regular y, when x is 2. So we need to know what 2 to the third power minus 4 times 2 is. That's actually pretty easy to do because those are both 8. 8 minus 8 is equal to 0. So we know that the point 2, 0 is on this curve, or on this line, rather. Now we also need to know what y prime is when x is 2. That will be 3 times 2 squared minus 4. Let's see, 3 times 2 squared is going to be 3 times 4, which is 12. And 12 minus 4 equals 8. So that's the slope of our line. So going up here, when x is equal to 2, the equation of our line will be y minus 0, again, equals the slope of 8 times x minus 2. And we don't have to worry about converting this into slope-intercept form because it basically already is because of the y minus 0 on the left-hand side. So we have y equals 8x minus 16, and that is the other equation of that line. If we wanted to get fancy right now, now might be a good time for us to actually graph the original equation and these two lines just to make sure those actually do work. I actually am going to do that really quick because it will not take a ton of time. This video might run a little longer because I'm going to do some extra things with the problems, but you can go ahead and skip around as you need to when you're doing these problems on your own. Negative 4x is there, and 8x minus 16. Always a good idea to check the work anyway that we're doing. I should make calculator cam a little bigger so we can actually see it. So here we have the original curve, and we have the 2 lines that we found. And if we graph this on a standard axis, we should be able to see the original cubic curve, like there. We should see negative 4x come through right there and touch right at 0. And then the other one is going to come through and touch at 2, 0 right there. There, perfect. We did it. Now, the other part of this question is they want to know what that intersection point is right there. Now, we could use the calculator for this. It's in the instructions, by the way. I haven't read it yet. What we're asked to do then is to determine the point of intersection for those 2 tangent lines. We could use the calculator for that, but since we have equations for both of those, it would be easier to just take those two equations and set them equal to each other. When does negative 4x equal 8x minus 16? Let's see. I would subtract 8x from both sides to solve this, and you would get negative 12x equals negative 16. And so x is going to be whatever 16 divided by 12 is, which is the same thing as 4 over 3, or 1.3 repeating. That's the x value. For the y value, we're going to need to plug that point into, well, either one of these equations would do, because they should have that same x value there. So I'll use the top one because it's a little easier. The y value is going to be negative 4 times whatever 4/3 is. I think fractions are a better choice here. Negative 16/3 is a good answer. That in decimal form will be negative 5.3 repeating. There you go. That's not a very nice answer, but that is what it is. It's the point 4/3 comma negative 16/3. And that kind of matches what I see on the graph, just eyeballing it really quick. It looks like a little bit more than 1 on x and a little bit less than 5 on y. That fits. Okay, let's move on to the next question. For each graph below in 3.162, we want to trace the graph on our paper, which is already here, and write the slope statement for f. I'm going to do this pretty briefly, and then I'm more interested in question number 2, sketching the graph of f prime using a different color. I really only care about question 2 here, so question 1 I'm just going to write down, and then I would suggest that you actually really think about question 2. On question A, the slope is, I just think it's important for you to notice that it is very negative at the start, right there, but then it is increasing towards 0. Just want to make a quick little slope statement there. When you get to the end of it, it's going to be pretty close to 0. For question B, the slope is negative and then 0. You can see negative here, and then it's 0 in the middle, and then it's positive again. The slope is continuously increasing. I'm just going to write always inc to save some space. And then question C, what I think you should notice is that it's very negative, and then it increases towards 0 right there, and then it starts decreasing again. So what it does is it starts negative, increases to 0, and then decreases. It's never positive is a good point to think about here. The slope on this line is never going to be a positive number. It's always going to be negative. This graph is always decreasing. That's a good way to think about that. Okay, so if we're going to draw, I'm going to use my orange pen for this to draw the actual slope lines. So we need a negative number that increases to 0. So our slope equation would look something like this. Kind of like that. For B, what I want you to notice is that the slope here is actually going to be a linear line because this slope is always increasing. It hits 0 at 2, but as long as you draw a straight line going like this, I think you're good to go. Recognizing that the derivative of this quadratic would just be a linear equation. In question C, that's a cubic function. Its derivative is going to be a quadratic. And it's a quadratic that's going to start negative, go up to 0, and then decrease again. So it'll look something like this. Like that. Just graphing the slopes. Okay. The next question is a review of our Riemann Sum thing we were doing back in the first and second chapters. We should keep this fresh in our heads as it becomes more and more applicable. We're going to write and evaluate a Riemann sum to estimate the area under the curve for from 1 to 8 using 10 left endpoint rectangles of equal width. We're just going to write it. I'm not going to bother. I'm going to evaluate on the calculator, but I don't care if you do that. I just think you should keep this formula in your mind. We're going to go from I equals 0 to n minus 1, in this case 9. What we are going to need is the delta x in this problem. The delta x is going to be 8 minus 1, which would be those two numbers there, 8 minus 1, divided by the number of rectangles, in this case 10. So that'll be 7 over 10. That's going to go in the front, because each one of those rectangles is going to have a width of 7/10 in order to make 10 rectangles from 1 to 8. And then inside here, we're going to multiply that times f of, our left endpoint is 1 plus our delta x, 7 over 10 I, like that. Now, if you wanted to get advanced, you could take this interior part of the function and plug it in for x into that little y equals 4 over x thing. So a better way to write this might be the sigma from I equals 0 to 9 of 7/10 times, in parentheses, 4 over 1 plus 7/10 I, like that. This you could put directly into a calculator and find the answer. I'm going to do that as fast as I humanly can on calculator cam, leaving the question right there to show you how to do this. So let's see. Now that we've already actually entered it in as one function, I'm just how I'm going to write it. So yeah, I'm going to put into y1, I'm going to put 7 over 10. Actually, no, I'm going to put the inside part of the parentheses there. So I'm going to make a fraction, 4 on top, 1 plus another fraction, 7 over 10, x on the bottom there. That's going to be the function part of this. Back on the home screen, I'm going to clear this out and open up my my F2 menu and find the summation notation thing there. I'm going to go from x equals 0 to 9. Inside here, I'm going to push alpha x to bring up a fraction and make 7/10. I'm going to multiply, whoops, not down there. I'm going to multiply 7/10 times y1, since we programmed our thing in there. And that should match about what I've got written right down in pen. And this answer will take a second to calculate. It's going to be about 9.69685, which is perfectly good for me. I'm going to call this problem good, 9.69686 or so. I should really technically put an approximate equal to there on that, but that's okay. Let's get calculator cam out of the way. Let's do some more problems. 3.164, we're going to sketch the graph of a function given the following information about its slope. So we need this graph to be, let's see, original function. F prime of x is greater than 0 means it's going to be increasing from 1 to 4. F prime of x being less than 0 means it's going to be decreasing from infinity to -1 and then after 4 to infinity. And it's going to have a local extrema at the points 1 and 4. So let's go ahead and make this happen. This should be pretty easy to do. I'm just going to make a quick sketch of a graph. I'm going to put the y-axis over here because I know that the kind of extremes happen at 1, 2, 3, and 4, like that. So we need this graph to increase until it hits 1. Then it's going to decrease until it hits 4, and then it's going to increase again. There you go, and that's all you really need to do. Since all the information we have is about the derivative, the y values up and down actually don't matter at all here, since you could take that blue function, slide it up and down wherever you want, and the slopes wouldn't change. The derivatives would still be the same thing, so like that. Speaking of derivatives, in 3.165, we have some more just basic power rule derivatives to do here. Let's see. We will need to write each equation first, so let's do that. I do not want to do C right now because I'm not really interested in trig identities being a big issue for anybody. So let's not worry about C. Let's just look at A for now. Okay, so the rest of these problems are totally doable if you rewrite them as polynomials. This first one here, y is equal to, well, that's an x to the negative second power inside of that 1/3 power. So what we have here is, let's see, we have x to the negative second power raised to the 1/3 power. And a better way to write that would be x to the negative 2/3 power, like that. That's how I would think about the original function. That means that the derivative, if you think about your power rule here, you'll bring that negative 2/3 down, you'll multiply it in front, and negative 2/3 will drop down by 1. Negative 2/3 minus 1 is going to be negative 5/3. Like that. And we can clean that answer up a little bit. I kind of don't like how the original answer is written. I'm going to keep negative 2 on the top of the fraction. 3 is on the bottom. And also on the bottom will be x to the positive 5/3, which I'm going to write as the third root of x to the 5th. And I think that's the best way to write that answer. Question B. The first thing we should do for question B is rewrite this. This is x times x to the 1/2 power. And what we can do there is we can actually add those exponents together, because this is x to the first power. 1 plus 1/2 would give us x to the 3/2 power, and that's the one I think we should take the derivative of. So that's what we'll do. Y prime here will bring your 3 over 2 down in front, times x to the 1/2 power, 3/2 minus 1. We could rewrite this a little better. We can keep 3 on the top. Actually, Square root of x stays on top too, because that's not a negative exponent, so this would be the best answer, I think, for that question. And I'm going to do d off to the side here so we have some room. We have y equals, well, I'm going to rethink about how we think about this problem here. I would say that's x to the negative first power times x plus 2. I like that a little better because now we can think about it as like a distributive property thing. We can rewrite this as, well, this would be x to the first power. So if we add those together, negative 1 plus 1, when we do the distribution, that's going to be x to the 0 power, which is just 1. And then we're going to have a plus 2 times x to the negative first would be what would happen when we do that distribution. This is a much easier thing to take the derivative of, so let's try that. Y prime here would be 0 for the constant 1, and then the next term, negative 1 times 2 would be negative 2. And then we would drop our degree down by 1 to get x to the negative second power. We can rewrite this as negative 2 on top, x squared on bottom, and call that good right there. Good. Let's move to the next question. 3.166 is asking us for the general antiderivative for each function below. So again, we're going to think backwards with this. This is the original function, so we are looking for the capital F of x. So we're looking for the function whose derivative would be that original right there. So again, the best way to start this is to go up a degree. So x to the 1/2 power should become x to the 3/2 power when you add 1. So we're taking that 1/2 and we are going to increase it up to 3/2. Now we need to think of what multiplies 3/2 times what would give us this 3 in front. That's what we need next. 3/2 times what equals 3. I got to really think about this for a minute. 3/2 times x equals 3. This is how I really visualize it in my head there. You could think about it like a little algebra problem. I believe that would be 2. Yeah, 2 would be enough. That would be it. Because the 2 and the 1/2 would cancel out, leaving just the 3. Okay. Now as far as the 7x goes, we'll do this kind of the same way. We'll leave the minus sign in. We'll take that x up to the second power. And we got to think 2 times what is 7? That's going to be 7 over 2 is a good way to make that happen. Because, again, the 2 and the 1/2 will cancel out, leaving the 7. That'll work. We got to put a plus c on this thing, too, because we're asking for the general antiderivative. So any derivative of that, capital F of x, will take you back to this function right there. Let's look at the same thing for b here. We got to think about our reverse trigonometric things here, capital F of x. Well, we know that the derivative of sine is cosine, so we'll put sine of x here. We'll leave the constant of 2 out in front of the sine x, and actually maybe we should change that to a negative because the derivative of cosine is negative sine. So let's make this minus 2 cosine of x. That would do the trick. There you go. Plus c. Don't forget your plus c on there also. Okay, let's look at 167, practicing our composite functions. Here we are getting ready for a skill that will involve us to recognize what the two functions that are working together to build a composite are. So for h of x, we're looking for f and g. F of x is, let's see, for the function, okay. Yes, where f is going to be the outside function and g is going to be the inside function. So the inside function I'm going to highlight in green to help you see it. Right there. Those are going to be your g of x's that are happening. So it's easy to write those first. G of x is going to be 3x minus 11. G of x is going to be 2 to the x minus 1. And here g of x is going to be 5 minus 2x. That's all there is to that. The outside function would be the thing that happens next to that inside part. I'll use red. F of x would be the cosine of x. In A, in B, f of x would be the third root of x, or the cube root of x. And in C, it's kind of interesting, but the outside function would be 3 to the x power. The idea here is if you took that g of x function and plugged it in for x into the f of x function, you'd have the complete composite h of x function. 3.168 is a question that's going to have us practice our limits algebraically, so let's try that. We might use a graph for a couple of these. But this is a good skill to keep working on as we go throughout this too. So 3.168a, I can already tell we're going to need some room for this problem, so I'm going to do this off to the side. We have the limit as x approaches 0 of the square root of 3 minus x minus the square root of 3 all over x. Like that. Now the first thing we had to check here is that can we plug in 0, and we can't. If we plug in 0 for x, we're going to have 0 on top and 0 on bottom. So we're going to have to do some manipulation to this. Usually with these square roots, the best way to do this is to multiply by the conjugate, 3 minus x plus the square root of 3, like that, over the square root of 3 minus x plus the square root of 3. It's going to look a little complicated, but it's just going to be whatever the top of the fraction is, or I guess wherever that little minus sign is, it's the same thing but a plus instead. Now what would happen, the reason why this works, is it's going to cancel out all of the radicals, which is cool, at least on top. When you multiply these two together, the square roots will cancel and you'll have 3 minus x. The inside and outside parts of that multiplication will both be the same thing, but they'll be opposites of each other, so they'll cancel. And the last things, the negative square root of 3 times square root of 3 is just going to be minus 3. And also what's going to happen on top is the 3 minus the 3 will become a 0 and cancel out. On the bottom, we're not going to multiply those together. We're going to leave them exactly as they currently are. Because remember, our goal at the end of this problem is to just be able to plug in 0 and get an answer. So what's going to happen here is we're going to have the limit as x approaches 0. We're going to have a negative x on top because the 3 and the negative 3 will cancel. And we're going to have an x on the bottom times the other stuff, 3 minus x plus the root of 3. These guys will now be able to cancel out, and now you actually can just plug in 0. This is the limit as x approaches 0 of negative 1 over the square root of 3 minus x plus the square root of 3. And you can just plug a 0 into this and then evaluate it in your head probably. This will be negative 1 over the square root of 3 plus the square root of 3. In other words, 2 roots of 3. And I would not go any further than that on your calculator. I would leave that answer exactly as it is. That's going to be A. For B, B is actually a really easy one to do right now because we can just plug in 2. The first thing you should check in a limit problem is if you actually can just plug in the number, and you absolutely can here. There's no problems with that. You would get 5 on top and negative 2 on bottom. That's the answer to that question. No problems at all. Question C is a just from the right question. I think this one is best answered if what you could do is you could try to plug in a number like 2.01 to this problem. And see what's going on. That would be the first thing. Actually, let's do that because that wouldn't be hard to do. I noticed right away that you have the same expression on the top and the bottom. Those are just going to balance out to be 1, honestly. So if we think about this, I'm going to bring calculator cam up for a moment. If you were to plug in 2.01 in for x here and here, you would just get, in both those cases, you would get 0.01, positive 0.01, and they would divide out to be positive 1. So those don't really affect anything. The only question remaining is what's 2.01 squared, and it's about 4. It's a little bit over 4. Now the idea here is if we did that with a number that was like 2.000000001 squared, we get a number that's even closer to 4. So the idea is that as our input number gets closer and closer to 2 from above, specifically from above, we are getting closer and closer to positive 4. So the answer here is 4. Alternatively, you could try graphing that original function, and you would see that same limit happen from the right. Specifically, you would get 4 there. Our last question here, question D, is what's going to happen when we plug in infinity into this. So what you really got to think about is what is e to the negative infinity power, because you would plug in infinity right there. Of course, plus 1. Now, since e is just a base number, it's 2.71 or so, let's just try a number like, hey, what is e raised to, I don't know, negative 100,000? And I think you'll find that the calculator is just going to give up and say it's basically 0. And that's true. When you raise to a negative infinity power, it's just basically going to go to 0. So this thing goes to 0, and your answer here is going to be 1. The limit is going to approach 1. And our last question on this set is going to be the definition of a derivative as a limit to write the equation for f prime. I am going to do this one the long way because I feel like it's been a while since we've done this. But honestly, using the power rule is much more efficient and easy. I mean, right now, you could tell me that f prime of x is equal to 2. Just using the power rule, and then you're done. But let's practice the long version of it. This is the limit as h approaches 0 of f of x plus h minus f of x all over h. So if we're going to plug this in, this is the limit as h approaches 0 of 2 times x plus h plus 9 minus, in parentheses, please, 2x plus 9, because that minus sign will be a factor later, over h. So what's going to happen here? You're going to have the limit as h approaches 0 of 2x plus 2h plus 9 minus 2x minus 9 over h. And look what's going to happen. The 2x goes away. The 9s go away. And what you're left with is the limit as h approaches 0 of 2h over h. The h's cancel. Now there's nothing happening there with h at all. So this just equals 2. And that's exactly what we saw at the beginning of the problem when we started it. It's actually not too bad to do. So, hey, cool. We went a little over 25 minutes with this one. It's a little longer than I intend homework problems to do, but all of these are good practice. Please make sure you're keeping up with your practice, because that's the biggest thing with calc students, is that you got to make sure you keep those rules going. You are doing a great job for making it to the end of this video. I'm very happy to have you in class or watching this video wherever you are. And I will see you in the next one. Keep it up. You are awesome. I'll see you.